Hello, everybody. Welcome to this webinar about FDS and cloudHPC. Thank you all for being part of this presentation. This is Ruggero Poletto who is speaking, and we are starting right now. We are on time with the presentation we said. So let's start with the slides. So, during the whole time of the presentation, you can actually have a look and interact with myself by using the chat you can find on the right-hand side of your of the video streaming. I hope the quality of the video is good enough, so please let me know in the chat if you're having troubles with that. First of all, a brief introduction of CFD Fair Service. We are a company. Our headquarters is in Italy, near Verona. We are focused in three main businesses area. The first one is software development, in particular as far as engineering is concerned. Second is consulting and engineering design, in particular in the civil engineering and mechanical applications. And the third one is the one we're going to talk about today is cloudHPC, in which we provide hardware resources to run simulations. As today we're going to be highly focused on FDS analysis and the scalability. Well, when running FDS simulations, but in general, when running simulations, someone wants to reach a very good scalability. It means that if I allocate a higher number, a bigger number of hardware resources, I want to reduce the total time required by the simulation to get completed. So this is like a goal which we would like to achieve. And today we are going to go through some definitions and we're going to see how we can achieve this goal using FDS and why cloudHPC is a good partner, is a good hardware provider in order to help us reaching this goal. First of all, we have some dictionary in order to be sure, a couple of definitions. First one is CPU. It's a word that identifies the parts of the hardware resources used for computation. And then there is RAM, which is just the memory. So it's again, is similar to CPU, except that the CPU is actually making the calculation. RAM, it is used to store the calculation, okay? Store the mesh data, for example. Well, what we said before is that if we want to achieve a good scalability, we want to reduce the total simulation time while we increase the number of hardware resources allocated for that particular simulation. So overall, we want to compare the speed up. So the speed up is the time required for the simulation with one single CPU, remember the definition we said before, divided by the time required for the simulation to complete with n CPU. This is the speed up we are providing to one particular simulation. Then there is the efficiency of the speed up, of the scalability, which is the speed up divided by n, divided then by the number of CPUs we are using to compute the simulation. So this is the efficiency. Speed up means how much we are accelerating our calculation as we allocate more and more hardware resources. Efficiency is a way to evaluate actually the efficiency that we are using for our hardware resources. Well, in general, what we notice is that as we increase the number of processors and CPU are used like synonyms in this particular presentation. As we increase this number of processors, we are linearly also increasing the speed up. Okay, so there is a linear relation between the processors and the speed up. This up to a certain threshold in which as we continuously increase the number of processor, we get a lower speed up. So this relation tends to be speed up. Well, when we start seeing this, let's say, no more linear relation between the core and the CPU allocated and the speed up, well, that means that we reached the maximum speed up we can achieve with that particular simulation. Uh, Obviously, the same is also valid for the efficiency, which works the other way around. In theory, we want efficiency to be 1 at all times. Okay, a 1 means 100% actually, and we see a drop as the speed up tends to become lower. Okay, we also have a drop of the efficiency, which tends to be from 1, it goes down to 0.9, 0.8. I mean, in theory, it can go to 0.5 and even lower than that, okay, depending on how we set up the scalability. Well, it's worth a while keeping in mind that speed up can be achieved into 2 different approaches. One is called multi-core, and the second one is called multi-threads. These 2 approaches may be available on your computer or maybe not available in your computer. And that's one side regarding the hardware resources. On the other hand, regarding the software we are using, well, the software can be implemented to use both these approaches, or just one or just the other. Okay, so it's a continuous relation between the hardware we are using, which makes available these 2 approaches, and the software we are using, which might be able to use only one of the 2 or both of them. Okay, so we are, at all times we need to know exactly which software we are using and which hardware we are using in order to define and to decide which of these 2 approaches we can use. On a Windows machine, for example, you can have a look at the approach the approach your machine makes available by pressing Ctrl Alt Delete and then going to the task manager and check number of cores and number of logical processor. Number of cores is tells you how many cores you have available in the multi-core approach. And the logical processor is the number of threads you have available in the multi-threads approach. So these are the hardware information that needs to be computed, needs to be evaluated when running a simulation. What's the difference between these 2 approaches? Well, the difference is quite simple. In the multi-core approach, we have our problem, our simulation. We have to split our simulation into smaller ones, okay, into sub-problems. Each of these sub-problems is allocated, is given to one particular core with his own RAM make available, okay? And so in this way, this particular core doesn't have to solve the whole simulation, but just part of the simulation. So actually, the problem to be solved by this core is smaller than the original one. And as a consequence, it can be solved in a shorter amount of time. Obviously, we start from a problem and we have to split the problem, to divide the problem into smaller ones. And in the end, we have to reconstruct from the solution, the partial solution coming from all the cores, we have to reconstruct the final solution we are applying to our simulation. So in this multi-core approach, there is a split, and at the end, there is a reconstruction of the simulation. And then there is a multi-thread approach. Multi-thread is a little bit more, let's say, articulated in the sense that we have our problem and we have our RAM, and we have these threads. They are all collaborating to solve the initial problem using a shared hardware resources, okay? So this second approach is more articulated from a hardware point of view, but from the user point of view, this is simple. This is easier than the first approach because we don't have to split our initial problem, our initial simulation into smaller ones, okay? We can assign all the simulation to the hardware sources. Well, the real problem is that we're going to see later, but the multi-core approach is more efficient. Okay, so even if we would like to use only multi-thread, well, if we did that, we wouldn't be as efficient. We wouldn't achieve a good scalability. So we need to apply a multi-core approach. So for this, we need to split the mesh. And in the next slides, we're going to see how we can split the mesh and do the problem in this way. Well, in FDS, if you open, let's say, the FDS file before actually executing it, you can see there are listed several commands, and each of these commands is an end followed by a specific command. Well, for the moment, we're going to see the mesh command, okay, which in general is has two name list. The first one is IJK, which defines the number of cells in X, Y, and Z direction. And the second name list is XB, which defines the cube, the geometry part where we are actually defining the mesh. So this XB means that we are defining this mesh in a cube that starts from X minimum 0 and X maximum 1, or y minimum, y minimum 0, y minimum 1, and the same also for z. Sorry, z minimum 0 and z maximum 1. So this is the volume where we are applying this mesh, which is 10 by 10 by 10. As we said before, in order to achieve a good scalability, we have to split our problem. So we have to split our mesh. And in FDS, this is something we have to do manually. So starting from our initial mesh, here you are, I generated 8 meshes. Each of them has 5 by 5 by 5. So it's a quarter of the initial, actually 1/8 of the initial mesh. Okay. And obviously, all of them, they don't act on the whole cube, on the whole volume, but just on an eighth of the initial volume. So from 0 to 0.5, 0.05, 0.05, the same 0.05, 0.05, 0.5, 1 in Z, and so on and so forth. In this way, we are redistributing the mesh into 8 smaller ones. Okay, this is an operation we have to do manually. Or if you're using some user interface such as Pyrosym or some other such as the mirror one, it is possible. There are functionalities to do that. There are split mesh functionalities that allows to help the users into this splitting operation. Well, if we want to be even more precise, we can define for each of the 8 meshes we generated this MPI process. Okay, this MPI process says that the processor number 0 is going to be assigned this first mesh. The processor or the CPU number 1 is going to be assigned this second mesh. CPU number 2, this third mesh, and so on and so forth. So when we assign this MPI process, we always start from 0 and we go up to the number of process minus 1 we want to allocate for these particular simulations. Okay, so overall we are using 8 different processes, 8 different CPUs, 8 different cores. They are all synonyms. They are all words that meaning the same. We are using this 2 or 3 words to have the same meaning in this case. Okay. Well, this MPI process parameter we have just seen is even more useful in this example. In this example, all the meshes have different size. All the meshes have a different number of cells to be computed. The first one has 17,000 cells. The second one has 5,000 cells, and the third one has 6,700 cells. Okay, if we applied MPI process 0, MPI process 1, and MPI process 2 at the third one, well, we would have the first mesh much bigger than the other. So the first core would have to compute a much bigger simulation than all the other cores. Okay, so in this case, we can use MPI process equals to 0 for the first one, and MPI process equals to 1 to the second and to the third. In this way, the first processor will have 17,000 cells, while the second one will have to compute 11,700 cells. In this way, we are kind of redistributing more evenly the workload between the processors. So it is easier to understand that the workload is actually the number of cells every processor has to compute. Okay, so in this case, we need to keep track on the number of cells assigned by each mesh and somehow calculate that and keep that in track in order to evenly distribute that between the cores. This is a more complex situation in which I have 8 meshes, okay, and they all have different size in terms of X, Y, and Z number of cells. So in the beginning, I plot this graph in which I just plot the number of cores and the number of the number of cells of each of these meshes, basically. In this case, we can see that there is mesh 7, which has approximately 100,000 cells, maybe 100,000 cells, while mesh 1 or mesh 2 have just 25,000 cells, so a much smaller amount. So again, using this MPI process and using that, let's say, correctly, we can distribute more evenly the number of cells between the processors, between the cores, and in this way, we are achieving a much better situation in which you can see all the processors over here are have between 75,000 and 100,000 cells. So a more evenly situation than the one we started from. So this parameter is very important in order also to redistribute the workload between the cells. Well, when we start a simulation on cloudHPC, we have some tools that are telling us how we are distributing the cells between the processors. Well, the first tool is an image. They are all images produced here at the bottom. The first one is this image over here, which represents the processor ID in the x-axis and the number of cells in the y-axis. It's called the processor load. It tells how many cells we are assigning for each processor we are using for the computational. In this case, you can see we have 6 meshes, and overall processor 0 has about 200,000 cells to compute. Processor 1 has a higher number of meshes, probably because in this case we use this MPI process parameter to assign more meshes to this processor 1. But as you can see, overall we are approximately with the same number of meshes, so 200,000. In this case, the workload between these two processors is quite equilibrated, okay? It means that we are assigning a similar workload to the two processors. It means that the simulation is going to reach a good scalability as far as this simulation is concerned. So this graph is a very good and very easy way to monitor and to have an idea on how the scalability, how the workload, the cells to compute are even if they are evenly distributed among the processors or not. The second graph is made available by FDS itself, in particular by the most recent version of FDS. It gives you an idea of the step size, so the time step that is computed for every iteration. As you can see, this is the log produced by FDS. FDS runs several iterations. It calls them time steps, and each time steps is a step in time ahead in order to compute the simulation. The user usually doesn't select what is the time advancement for each iteration, okay? Because that is computed automatically by FDS. And in this graph, the green line represents the time advancement in your simulation, okay? Usually we don't want this green line to become very, very small value. Usually it's between 10 to minus 3, 10 to minus 2. That is, let's say, a good range. If we get a range lower than this, it means that there is a problem in our simulation. Probably there is a location, a place, a point in our simulation which the velocity magnitude is becoming very, very high. Well, it's this is something often usually they don't keep track of, but it's worth a while having a look at this graph and in particular at the step size in order to understand if the time step is becoming too small. So I suggest to move and to get to modify a little bit the setup, the boundary conditions of the simulation, or to modify the mesh, okay, of your simulation because there is something correct. The third output that we are providing is the .out file. Okay, among the logs, there are two files that FDS produce, which are very, very important. The first is the .log file, is the output file we are used to with the time step and the simulation time performed. And then there is the out file. It's worth a while looking at that file in particular if you're getting troubles with the time step, because it can tell us in which mesh we are having a problem, and which mesh the velocity magnitude is becoming huge, is becoming very, very big. Okay, so that tells us where we have to operate in order to fix our simulation, in order to improve our simulation scalability. I also add here, it's a little bit off topic, and this slide which speaks about FDS instability. This is quite a common error I've seen in quite a few simulations, and I would like also to give you some hint about how to solve that. Basically, sometimes if there are incorrect setup of your simulation, you can run into this warning, minimum density. There is a value, and it says that this density has been clipped in mesh number 7, 6, whatever is your simulation. And after a few times you see this warning, often there is a numerical instability and FDS is automatically stopped. Well, this is, let's say, often an issue with the mesh we set up for the simulation. And we can actually see in smokeview where this error is happening. Well, if we load the result in smokeview, there is this plot 3D value in smokeview to load, and then we just load the last time step, and we have a list of all the meshes where we can load this variable. Well, and going one by one, we can actually see here a report of the files of the quantities that have been calculated in the simulation. And in here you can see we have a very low value of pressure. Consider that the pressure, the environmental pressure, is about 1 bar, so 100,000 pascals. Pressure fluctuations usually are approximately, let's say, 10,000 pascals, so 0.1 bar. And in here we have a minimum pressure of minus 94,000 pascals. So it's a very big fluctuations. Also, temperature is becoming very low, minus 127 degrees Celsius. That's unfeasible, unphysical. So FDS is calculating that, but probably there is something weird, let's say, to do. And also the velocity which should be something like 10, 30, 40 meters per second. In here we are getting 94,000 meters per second, so completely unfeasible, completely unphysical. So it doesn't respect the physics of the problem. Well, in this case, now that we know that the clip is in mesh 7, we can have a look at that. These are the heat the hints to follow in order to fix the problem. So probably there is an aspect ratio between two neighboring meshes, like mesh 7 and mesh 6, for example, in which we have a ratio larger than 2 to 1. So every two meshes, two cells in mesh 7, there is just one cell in mesh 6. That is okay. But if we have six cells in mesh 7 and one cell in mesh 6, well, in that case, probably we have to refine a little bit neighboring meshes. Another thing is that there might be a small opening towards like outside, or a small opening between two zones of our simulation. Well, in that case, through that small opening, there might be a very high speeds. Okay, so we might reduce or remove these small openings, or increase them in size. We might have in our simulation a sudden releasing heat release rate. Usually this doesn't really happen, doesn't really apply if we are following the HRR calculation provided by the British standard or the Italian regulations, because in that case we are imposing this heat release rate. There might be other issues with removing or adding some obstructions, or to simulate doors opening or doors closing using the control command. In that case, we can just, let's say, have a look at that and probably slightly move the obstruction to a different mesh, or slightly refine the mesh. If we use a custom fuel, well, we might have set a very high molecular weight. So we might go back to a lower molecular weight, maybe duplicate the fuel's species we are simulating. Or in the end, there might be an imbalanced flow rate. So we might have some inflow into the domain, and we may not have an opening somewhere else, which is allowing the inflow to go outside of the domain. Okay, remember that every time we have an inflow, there must be an outflow somewhere else. Okay, this is an easy, a logical happening, a logical condition we have to satisfy when running a CFD simulation. Well, let's go back to the scalability. Well, in FDS, when we execute a simulation, we can execute it then using multi-core or multi-thread approach, we said. Well, to execute it multi-core, we have a command to execute it, which is npi-exec minus np, the number of cores we want to assign for the simulation. FDS command, and the file name .fds, which we want to use for the simulation. For the multi-thread approach, actually everything is easier, because we just have to set this OMP num threads variable equals to 4, 6, whatever number of threads we want to use, and eventually we want to execute the simulation. Obviously, we can combine the two by setting this OMP num threads variable first, and then executing FDS with npi-exec. And well, when we do that, FDS in the log usually provides us the information of how many MPI process and how many threads it's using. In this particular case, we are using 4 MPI process and 2 threads. Okay, so every simulation has this particular information which the user has to take care of. On the cloudHPC instead, everything is easier. Okay, it's easier because we can decide the hardware we want to use, and according to the hardware, we can decide if we want multi-thread and multi-core, or just one of the two. Okay. In particular, if under RAM we select high CPU, standard, or high MEM, we are using an approach which is at the same time multi-thread and multi-core. If instead we select high core, we are just using a multi-core approach. Okay. As a consequence, this influences the number of virtual CPUs we are selecting for our simulation. Okay, if we set RAM to be high core, well, in that case, we selected the number of MPI process and we multiply that by 1. And that is the number of virtual CPUs we want to use to execute our simulation. If instead we select high CPU RAM, which is high CPU standard or high MEM, well, in that case, MPI process, the number of MPI process must be multiplied by 2, so that we are assigning 2 threads for each core when running the simulation. Well, we can actually have a look and have a test. So I just enter the cloudHPC website. This is the cloudhpc.cloud. That is the reference website. And I sign in. So in here, I sign in with a general user. Well, in order to execute the simulation, I just go to storage. I press plus. And in here, I can drag and drop a file I previously defined for our simulation. So this is a staircase simulation file. I just press save. And here I can see the FDS file available on my system. Pressing this edit button, I can enter the details of this file and have a look on how this file has been configured in order to run the simulation. As we said before, I just want to see the mesh command. If I just double click, if you see, it automatically highlights all the meshes. There are no other meshes in this simulation. All these 8 meshes, 2, 4, 6, and 8, they all have exactly the same size. ijk equals to 28, 16, 114. So in theory, I can use, on the practical side, I can use 8 cores for this simulation, no more than that. And since they are the same size, I can set the MPI process equals to 0 for the first one, equals to 1 to the second one, and I just proceed 2, 3, 4, 5, 6, and 7 as the last one. Okay, so in here I am assigning this every mesh to one single core. At the bottom, I press save. So this is my file ready to run. I just now go to simulation, I press plus, and well, the first thing I select is RAM, and I can select high core, and in that case, I'm running my case on 8 CPU. Okay, this because these 8 CPUs for a high core, they just represent physical cores. Otherwise, I can select high CPU. In that case, I have 16 to select because I am selecting 8 cores, and for each of these cores, I'm selecting 2 threads. Okay, so 16. Well, let's just allocate 8 cores. Under folder, I'm selecting my FDS file, and under script, I just select the FDS version appropriate for this simulation, which is 6.7.5. I press save, and automatically my simulation starts. In the beginning, the simulation is in pending, okay? Usually this pending status doesn't last too long, it's just a few seconds, and automatically the simulation becomes running. So we just wait. Here it is. Okay, now we are in running mode. I just refresh the page, and well, the system automatically takes into in charge the simulation and starts running it. Actually, it takes 2 or 3 minutes before actually running a simulation because every analysis is performed on a dedicated virtual machine. This means that it takes a couple of minutes to allocate the virtual machine, and once it does that, we can actually start the simulation. The system can actually start the simulation. So let's just wait a little bit for the virtual machine to be allocated, and let's have a look at what actually is happening when the simulation starts and what monitor data I can have in order to monitor, let's say, the scalability of my simulation. So basically the graph we saw before with the equivalence of the cell load assigned per each core, and also the output file, for example. So I just go back in here into my simulation page. I just can now enter and yeah, just give it 1 second for the virtual simulation for the virtual machine to be completely defined and for the simulation to start. Okay, there it is. Virtual machine is about to be completed and eventually the simulation is going to start. Yeah, if you see, once the virtual machine this is the part in which we are generating the virtual machine. Once that is done, everything proceeds quite quickly, let's say, and in a few seconds the simulation is going to start. So yeah, we everything is ready for the calculation to start. So yeah, now this is means that the simulation is now starting. So consider that I set up at 11:33 the simulation to start, and now it's 11:35, and the simulation is already starting. So literally 2 minutes before the simulation is actually starting. When the simulation is starting, here at the bottom you can see a remote desktop. There is this folder which contains the FDS results which are computed, and there is a smoke view over here. So I just double click that and I can actually see smoke view. So the case is the one which has been highlighted also in the introduction of the webinar. It's just a simple star case. Okay, in here I can actually have a look at the file which is set up here, and if I want, I can activate grid lines. Okay, so I can actually see the grids to which we are applying the simulation. If I now just refresh the page, probably it takes a few more seconds. I just refresh it once again, because once I refresh it, I can see under images everything I said before. So I just go back and move back here. Yeah, there it is. So this first graph represents the time step. Okay, so I just have to go and see the step size, the green line. Well, the green line usually starts with a higher value, and as the HRR curve becomes higher and higher, you see it tends to decrease a little bit. That's quite normal. We have to pay attention that this value doesn't go to very low, let's say below 10 to minus 3. So that's worth a while keeping a look. This represents the cell distribution between the cores. We have one mesh per each core. And as you can see, it's about 65,000 cells per each core. And yeah, it's evenly distributed, obviously, because we just have all the meshes are exactly the same. In here, I can visualize the log. Instead, on the right hand, I can visualize the output, okay? Sorry, produced by FDS. The first part is quite interesting as well because it gives us information about simulation parameter and what we are producing. In this particular case, we have air, okay, and we are burning propane, and we have a certain number of species involved, and obviously we are monitoring carbon dioxides with a certain molecular weights, and so on and so forth. So it's worth a while, let's say, keeping a look at that, also to see if we set correctly all the parameters involved with the simulations. And all right, this is a summary of the surfaces. Like in the file, we have HRR per unit of area of 500, which is equivalent to a propane flux of 1.12 e 10 to minus 2 kilograms per second per square meters. Open, which is passive vent to the atmosphere, evacuation flow. Yeah, so this is quite good devices. It's very good to monitor the simulation, and it tells us also for each mesh we set up for our simulation, let's say the convergence of that particular mesh. So having a look at that, if we see some weird values, we can actually detect where, in which mesh we are getting these weird values, and eventually apply a solution to that. Another thing which is quite common and quite useful to monitor is this CPU usage graph. The red line represents the CPU used by the users, and we want that to be as close to 100% as possible. In our case, obviously, in the beginning is a little bit lower, but then you can see it's one straight line at 100%. This means that I am using completely the CPU, and I am using that correctly because 100% of the CPU is dedicated to the FDS simulation. So yeah, the simulation now is proceeding, and well, for this moment, I'm gonna stop it because we don't want to get to the very end of that. So I just go back to my presentation. So yeah, we work very close with Pyrosim and Thunderhead Engineering in particular, which I thank as always. In the past 2 years in Pyrosim, it is possible for you to run FDS simulation on the cloud directly on Pyrosim. So without, let's say, moving to a different, sorry without going to a different opening the website, but directly on Pyrosim you can under execute and simulation in the cloud run the FDS analysis on the cloud. Obviously, you have to select the cloud provider to be CFD fair, which is our company. You have to select to write the API key that is provided once you create a new CFD Fair Service account. So you follow the account creation procedure and you are going to be assigned a CPU. And then obviously you have to select FDS version, number of virtual CPUs and memory options as we said. As we said so far, then you press OK, and automatically the simulation runs on the cloud. With this is everything for the webinar we were meant to have today. I invite you to get in contact with us via our email addresses or by registering to the cloudHPC website in this link. Sorry for the cough. So if you have questions, if you want to get in touch with us, feel free to send emails. And with this, I can say the webinar is over for today. I see no questions in the chat. So keep in touch and I hope everything is all right and see you on the Cloud HPC. Bye bye.